Hello and welcome everybody to today's lecture about protection in electrical power systems. The focus today is in earth fault protection and especially on earth fault relaying with Wattmetric relays, which are the most common and widely dispersed relays. I will give you an example of a medium voltage network which consists of a transformer feeding into a 20 kV bus bar. Then there is a grid, let's imagine it is a cable grid connected to it with a capacitive earth fault current of 300 amps. And we set the arc suppression coil to 3% overcompensated, so the nominal current of this arc suppression coil is 309 amps. Now there is one faulty line which consists of 10 kilometers of 3 single-phase cables, and at the end we have a short circuit. Now let's start with the positive sequence system. The positive sequence system is known to everybody of us because a three-phase short circuit is controlled by the vital elements of this three-phase system, which is the transformer impedance and the line impedance. Now let's concentrate on these. The transformer impedance can be calculated as shown above, and the value is 2.4 ohms. The same applies to the line impedance. The line impedance is the specific impedance of the line multiplied with the length of the line, and that comes out as 1.3 ohms. So that was the positive sequence system. The negative sequence system, easy to remember, is in practical applications identical to the positive one. So we have these two, we connect them in series, and the last missing link is the zero sequence system, which is shown here. And now we go into greater details. Of further interest will be 2 points. The red one is the fault point, and the blue one, further to the left, is the relay location. Now let's see what is the zero impedance of the cable. So the zero impedance of the cable is given by this well-known formula, specific impedance times line length, and that comes out in this case as 4.4 ohms. But the cable also has, in this case, this is important, it has transverse impedances, these capacitive reactance, and they are calculated as follows. This capacitance is given by 3 times phase voltage divided by the earth fault current, and then this comes out as 25 amps, and accordingly the transverse, this shunt reactance is 1380 ohms, or placed on the two ends left and right of the cable, we have this value as indicated here. So the next element is the healthy network, as we call it. The healthy network impedance is again a capacitive reactance, which is given by the well-known formula 3 times phase voltage divided by earth fault current, and in this case it is the difference of the total earth fault current minus the capacitive currents of the faulty cable. In this case is 275 amps. And that finally leads us to a reactance of 125 ohms. So the remaining element now is the transformer. Again, we have this well-known formula, and it comes out as 4.8 ohms. And now the critical element is the arc suppression coil. The arc suppression coil has again a reactance, and this time an inductive reactance, of 3 times the phase voltage divided by the current, the nominal current of this arc suppression coil. In this case it comes out as 309 amps, and altogether it's 111.7 ohms. So this is the main part of the arc suppression coil, but also there is one smaller element which in many cases can be neglected, but not for Wattmetric relays. This is the resistance, or the equivalent of the losses, the thermal losses of these arc suppression coils, and that's given by 3 times phase voltage divided by the losses, and that is finally 9900 ohms. Now we have the full picture. As you see, the positive sequence, negative sequence, zero sequence, and now we go into the calculation. First, I want to simplify with you the calculation, and that means we omit all series reactances which are below 5 ohms or 10 ohms, and also the shunt impedances which are above 5,000 ohms. All these are neglected. I indicate this in gray and then I take them just out. Now it is a simple equivalent circuit, and we start with the parallel capacitances as indicated in the red circle. So it's the parallel connection of these three capacitances, and also they are again in parallel to the reactance, the inductive reactance. And finally, this is the value for the zero sequence reactance, and that comes out as 3,892 ohms. The current accordingly is just phase voltage divided by this value, comes out as 3 amps. This is the zero sequence current, and the real fault current is 3 times that value. It is 9 amps. By the way, if you check, we had the arc suppression coil set to 309 amps. The capacitances gave 300 amps, so the difference is 9 amps, and that is in line with this. Now, let's see what happens at the fault point. That was the 9 amps. And now what is the relay given? So the relays sees the current that are fed from the left side into the feeder. That is on one side the inductive current, on the other side it's the residual capacitive current, and they are calculated here. First, the reactive current from the arc suppression coil comes out as, you can see here, as 309 amps, which was the set value. And for the capacitances we have to add this according to the phasor law of addition with a current of 375 amps. Altogether it's a current of 34 amps at the relay, which is not the same as at the fault point, and that must be kept in mind because this increase in current, in reactive current, makes it difficult for the relays to find a good discrimination. I will show this here, and we should add now this normally neglected resistive current, the wattmetric current, which is given by the losses of the arc suppression coil. That comes out as 3.5 amps in the zero sequence system. So, as it was shown, the protection relay at the bus bar looking into the feeder sees a reactive current of inductive type of 34 amps and a resistive current of 3.5 amps. And the resistive current is the decisive one. So the relay will do the following. We measure the phase displacement voltage, the voltage between the system neutral and ground, and then we compare it to the phase angle of the resulting current, which is made up of the inductive current plus the resistive current, and that is altogether the zero sequence current. So now, this critical angle, which I design here as delta, is the critical one that divides the relays that look into a faulty cable, where we transport this resistive current, and the healthy cables where you only have a reactive currents. So it is the angle which is very small that tells if it is not 90 degrees, it's faulty. If it is exactly 90 degrees, it's a healthy line. Now let's see, this small angle, what is it made up? It's the arctank of the resistive current divided by the residual reactive currents, and then we demand that the relay setting should be 50% below it, so that we have enough discrimination margin for safe and secure picking up of the relay. And in this case we see here that these values are very, very, very small. So if you take it in terms of time, the angle of 2.9 degrees electrical correspond to a time lag or time shift of 180 microseconds. So this is very demanding for the relays to measure. And if in reality this angle is too low or the relays will not pick up correctly, then there is just one chance for the wattmetric relays. We should increase this resistive current by adding further resistances in parallel to the loss-related resistance of the arc suppression coil. So this was today's lecture about earth fault relaying and the chapter about Wattmetric relays. So I thank you very much, and I'm looking forward for our next lecture. Thank you very much.